Hello and welcome. Today we're going to tackle a true classic, a problem from a physics textbook that has been a rite of passage for students for decades. So let's just dive right in, shall we? We're going to break down the deep connection between potential energy, force, and the actual shape of a physical field. If you've ever studied physics seriously, you know this book. Irodov is legendary. And this problem, 1.132, it's just a perfect way to really get your head around how a potential energy function, which is really just a bunch of numbers in space, defines the force field that a particle actually feels. It's where the math really comes to life. Okay, so here's our mission. We're given this potential energy, U, that depend on where a particle is. And notice those two constants, alpha and beta. The problem makes a huge point of saying they're positive, but they are different from each other. Now that little detail, trust me, it's the key to this whole thing. Our job is to figure out two things. Is the force central, and what do the maps of this field actually look like? To get this done, we've got a really clear roadmap. First, we're going to grab the main tool that turns potential into force. Then, we'll use it to check if the force is central. After that, we'll get into the fun part, mapping the field's geometry. And finally, we'll wrap up and see what we've discovered. First things first, before we can answer a single question about the force, well, we need to actually find the force. And lucky for us, physics gives us a really beautiful and direct way to do exactly that. This right here, this is it. This is our master key for the whole problem. It says the force vector F is the negative gradient of the potential energy U. Now, the gradient itself, that little upside-down triangle U, that's a vector that points in the direction where the potential energy increases the fastest. It basically points uphill. So the negative gradient points in the direction where potential energy decreases the fastest. It's like a ball on a hill. The force of gravity pushes it along the steepest path down. Same idea. Now, I know the word gradient can sound a little intimidating, but it's really just a recipe with a few simple steps. First, we take the partial derivative of u with respect to x. That just means we see how u changes only along the x-axis, and we pretend y is just some number for a second. Then we do the exact same thing for y to get the y component. And then we just stick them together to build our force vector. That's all there is to it. So let's actually apply those steps to our problem. When we take the partial derivative with respect to x, that whole beta y squared term is treated like a constant, so poof, it vanishes. We're left with just minus 2 alpha x. Same story for the y component. The alpha x squared term vanishes, leaving us with minus 2 beta y. And there you have it, our force vector. Now we can actually start answering the questions. All right, with our force vector in hand, we are ready for part A of the problem. Is this force field central? Is the force on a particle always pointing directly towards or away from the middle, the origin? So what even is a central force? Well, the perfect example is gravity from the sun. No matter where a planet is in its orbit, the force of gravity pulls it directly towards the sun's center. It's always pointed right along that line connecting the two. That's a central force. So how do we test this with math? Well, for a force to be central, its vector has to be parallel to the position vector r. This just means the slope of the force vector, Fy over Fx, has to be the same as the slope of the position vector, y over x. But look what happens with our force. When we calculate the ratio, Fy over Fx, we get this extra little term out front, beta over alpha. And this is the moment it all clicks into place for part A. Because the problem explicitly told us that alpha is not equal to beta, that ratio beta over alpha isn't 1. And that means the force vector and the position vector are not pointing along the same line. So nope, the field is not central. And this isn't just a math trick. It means something physically important. For instance, in a central force field, a particle's angular momentum is always conserved. Here, it wouldn't be. Okay, part A is in the bag. Let's move on to part B. First up, we need to find the shape of the equipotential surfaces. The best way to think about this is like we're creating a topographical map of our energy field. So an equipotential surface is just all the points where the potential energy U has the exact same value. It's just like the contour lines on a hiking map show you all the points at the same altitude. If you walk along a contour line, you aren't going uphill or downhill. Same thing here. A particle can move along one of these surfaces and the field does zero work on it. And finding the equation for these surfaces is, believe it or not, super straightforward. We just take our function for U, and we just set it equal to some constant value. We'll just call it c. That's it. So, what shape does this equation describe? Well, if you remember your geometry, for any positive c, this is the standard equation for an ellipse. And it's an ellipse. not a perfect circle, precisely because alpha and beta are different. It means the potential gets steeper differently along the x and y axes, which squishes the shape. And just like that, we have the first half of our answer for part D. All right, time for the final piece of this puzzle. We need to find the surfaces where the magnitude of the force is constant. Now, this is different from constant potential energy. This is all about finding where the push or pull of the field has the same strength everywhere. To figure this out, we first need to get an expression for the magnitude of our force vector. We just used the Pythagorean theorem for this. But here's a pro tip for you. It is almost always easier to work with the magnitude squared, so you can avoid dealing with a messy square root. It just makes the algebra way cleaner. So we square our force components, and we get this expression right here. And now we do the exact same trick as before. We just set this whole thing equal to a constant. Let's call it k. This equation now represents every single point xy where the force has the same magnitude. And would you look at that? We have another equation for a family of ellipses. So the surfaces of constant force are also ellipses. But here's the subtle and really interesting part. The parameters are alpha squared and beta squared, not just alpha and beta. It's a key little difference. So we did it. We've taken this problem apart piece by piece and found all the answers. Let's just take a quick second to pull it all back together and look at the complete picture of this force field we've just uncovered. This table sums up what we found for part B perfectly. Both the surfaces of constant potential and the surfaces of constant force are ellipses, but they're different families of ellipses. The specific shape of one is set by alpha and beta, while the shape of the other is set by alpha squared and beta squared. So what are the big takeaways here? First and foremost, that master key. Force is the negative gradient of potential. You absolutely have to know that. Second, we saw how a non-symmetrical potential automatically creates a non-central force. And third, we discovered how that asymmetry physically carves out the geometry of the field into these nested ellipses for both potential and for force. So really, the crucial point, the big idea, is that this simple mathematical link between potential energy and force isn't just some abstract formula. It's the blueprint that dictates the entire structure and geometry of the physical field itself. And I'll leave you with a final thought to really lock this in. We proved this field wasn't central because alpha and beta were different. So what if they were the same? What would that mean for the force field? And what familiar shape would those ellipses turn into then? Think about it. Thanks for joining me on this deep dive.